Okay, the purpose of this video is to give you a quick and I hope clarifying picture for the upcoming exam. The first idea, ID important lessons in each problem. And I want to also ID key equations. I expect you to know. I think there were some legitimate concerns expressed about that, and let me try to hit those concerns head on. So in the first problem, it's a heat transfer problem from a warm temperature to a cold temperature with a variety of resistances, both convective and conductive resistance. Remember, convective resistance is due to convection, bulk motion of flow, meaning macroscopic motion, not microscopic or molecular level motion. So as we go through this, the solution explains the overall setup. And I think if you get issues like the area clarified, the temperatures clear, the geometry straightforward, you can then look up the average temperature to get properties of components such as density, thermal conductivity, and you're well on your way. This particular equation I will not give you, and I expect you to know it. I also would expect you to know this equation. This particular problem is straightforward, and I think the primary lesson learned from this is this idea of controlling resistances. Know what that means. Know how to identify it inside the resistance makeup. Moving to the next problem. I think the critical element in this problem is the need to understand this drawing, acknowledging that the maximum temperature exists at the center. So if you were to draw it like a hill, this point would represent the heater temperature, with heat flowing downhill to lower temperatures, whether it be a TI or even further down, it looks like, because it's at -10 as opposed to 5, to T infinity. Once you have that understood, and you can write the standard resistance equations, I do expect that you'd be able to write this equation, so I would not give that. The next relatively straightforward step is to vary variables such as K, the resistance to contact, and H. Recognize that the Q prime and the R primes are per unit length items. As you go forward into the next problem, right away, I think you want to ask yourself, how can I attack this? And since it's asking for how a value of temperature changes over time, I want you to right away think lump capacitance. The only complication in this problem is that our normal Biot number, which is defined as h length scale over k sub s for the solid, where this length scale is usually the volume divided by the air surface area. This h is no longer sufficient. We have to worry about the total resistance of both h as well as a thin layer, this dielectric layer, and that's the only complication in this. I would have preferred that they not label this an L, but rather call it a T for thickness as a point of clarification. As you walk through the problem, I think it's straightforward as long as you get this relationship. And these relationships I would expect you to know, boxed in red. This relationship in blue, I do not expect you to memorize, and I would provide that for transient conduction lumped capacitance analysis. Once you get through a confirmation of the Biot number and you've calculated the overall U, it's relatively plug and chug to get the final answer of time. In the fourth problem, you're cooling air, and your question is how long does this pipe need to be? So remember, get clarity on how this looks and get a sense of the flow. In the solution, we try to break it down to a simple pipe. This equation that I draw in red, I would provide for you. But I would expect you to know this equation right off the bat. Okay, so that would be on your equation sheets or memorized. As you go through this problem, there's another equation that I would provide that did this bolter. Once you calculate the internal heat transfer coefficient, you can go forward and calculate UA with the L remaining unknown. Use this original equation to then solve for L. The pressure drop that they calculate in this problem is a bit complicated. We already know that it's rho G HL or gamma HL or rho G LD E squared over 2G. Oh, almost forgot the friction factor. The G's cancel. The friction factor can be achieved by either this equation or Moody. So I hope it's clear. I would provide this and this, but you would need to know items like that and this. The fifth item is a flow heat transfer across a cylinder. We're asked to calculate the rate of heat transfer per unit length using a particular correlation. Once again, I would provide that for you. This problem is relatively straightforward. It does involve a relatively complicated equation that I would certainly give you. And it goes pretty much as a plug and chug throughout the process. And the intent is to compare how engine oil, water, and air would compare. Moving to the final problems. Problem 6 is very similar in nature to the blood problem, blood heat exchanger problem. It is a shell and tube heat exchanger though, as opposed to a strictly unmixed cross flow. So as you walk through this problem, I think the key issue or concept to be able to do is to be able to write down a temperature versus location diagram and be clear about the shell and tube heat exchanger, the 1 shell pass, the 8 tube passes, and the 10 tubes. As you go through this, you will recognize that we're going to focus on the epsilon NTU method. Along the way, though, we'll apply the first law, and I would expect you to know that. I would expect you to know the definitions of CR. I would expect you to know the definition of NTU. And this is essentially the C min delta T min divided by C min delta T max. And I would expect you to know these relationships. This entire section here, again, I want to focus on red to make sure it's clear to you what I expect you to know, or what I expect you to know that I will provide. That entire group of equations I would provide for you. As you go forward, I would expect you to know this new definition if you want to use Reynolds number with mass flow rate. The Dittus-Boelter is back again. The key idea in that, though, was to make sure that you identified the right number of tubes to reduce the mass flow rate per tube. As I mentioned in class, I've made that mistake a few times. The rest of it is essentially an NTU utilizing this NTU value down here to solve for the remaining last unknown, which is the length. Finally, in this particular extended surface problem, we're looking at a comparison between a smooth surface and a thin surface. Equations like this I would not expect you to know. We've not spent enough time memorizing them, but I would expect you to know how to implement this problem. Notice how there are definitions, such as this, that also need to be known. Once again, I would provide those for you, these critical equations. And it all starts with this, so that you can eventually get to the overall heat transfer coefficient, which is what they wanted to see at the end of this problem. The last two problems are straightforward, and I would expect you to be able to do the calculations and to know all the critical calculations. In particular, this relationship, these isentropic relationships, should be on your sheets. I will not provide those. Once again, each of these problems is nearly or very similar to the homework problems that you've done. If you have questions, please let me know. I hope this was useful. I try to be slow at times, I hope, to clarify which equations are important and which equations I expect you to know and which equations you should expect that I will provide you. In summary, I would say that in preparation, you should focus on the basic equations of conservation of energy, entropy balance, thermal resistance, and I think you'll be fine. Good luck.